Heisenberg's uncertainty principle states that one cannot know for certain two related properties of a particle, such as position and momentum, at once, and the more you know about one, the less certain the other becomes. It's incredibly important in our universe and explains so many natural phenomena, such as light diffraction, virtual particles, why electrons don't fall into the atomic nucleus, and so many more. However, many misconceptions still surround it, the main one being that it is caused by a flawed measuring process. Throw out any garbage you learn about how the uncertainty occurs, because Heisenberg discovered that it arises due to the very nature of matter itself, not by some lousy measuring or whatever. This innate nature is what is known as wave-particle duality, meaning matter behaves both as a particle and a wave. With the de Broglie equation, we can measure the exact wavelength of any given object. But since everything in our daily lives is so massive, this wavelength is incredibly small. A baseball tossed up into the air only has a wavelength of about a billionth, trillionth meters. However, smaller particles, such as photons or electrons, have wavelengths that are incredibly large relative to their size. And thus, since a wave occupies many points at once, the particle can be in more than one position, one state, at once. This is what is known in quantum mechanics as a superposition. So a particle can be at point A with momentum x, or at point B with momentum y, and both would be equally valid states. The interesting thing is, once you measure any aspect of the particle, such as position or momentum, the superposition vanishes, and you're left with just that single state. Wait, we just found which state the particle is in, and thus we now know all of its properties, right? Wrong. See, the thing is, position and momentum are independent variables. Knowing one tells you nothing about the other. But why is that? Let me explain. Remember the de Broglie equation I talked about earlier? By using it, we can directly relate any momentum to a wave, meaning we can represent momentum as a wave. For any given wave, there are many possible positions, some more likely than others based on that point's amplitude. But if we want to pinpoint the position, we can add lots of different waves, so that one wave's crest cancels out another's trough until it gets essentially flattened and we are more and more certain of the most likely position for the particle. But let's look back at what we did to get here. We added different waves, and as we've seen previously, a wave can be used to represent momentum, meaning we just combine different momentums to be more certain of the position. But a particle can't have more than one momentum once it leaves the superposition. So which one of the momentums we added was the particle's original momentum? There's no way to be certain.